Please go ahead.
Yeah. Cool. So hello everyone. Today, your Professor Nima has already introduced me. I'm Chandan. I'm from the University of Bremen, and I'm going to present our paper, which is called veriSIMPLER, which is an automated formal verification methodology, and it is for the simpler magic tool, which is from Professor Shahar Kowatinsky group. And we will see how did we formally verify basically the mapping obtained from this tool. Our paper was published in TCAS-I, and this work was basically done in collaboration with Khushbu Chalar. They are from University of Bremen. Simranjit at that time was affiliated to Indian Institute of Technology, Bombay. Hassan is a postdoc in our group. He is also with the German Research Center for Artificial Intelligence. And then Professor Rainer Leupers from RWTH, Fahad, and Professor Rolf Drexler. I will skip this slide because Professor has already introduced me. Just a brief idea, like I wanted to tell what our group does. So we mostly do formal verification, but we also do a lot of other things like you have basically testing. We also work on emerging technologies where we look into hardware security, approximate computing, in-memory computing, and we also do some work related to using reconfigurable fetch. This is our group. We are a large group. We have around 60 people, and this group is both from University of Bremen and the German Research Center for Artificial Intelligence. So in total, we are 60 people. I'm here. I don't know if you can see my pointer, but okay. So since this talk is going to be on verification, I just want to tell that in today's world, while designs are becoming much and much more complex, the idea is how do we test whether what we are designing is correct or not? And one of the methods that can be used to do that is called simulation. Now, simulation is quite simple in nature because what you can do is you can take a few test vectors and you can test whether the design is giving you the correct outputs or not. But the idea is that the coverage obtained is very low. There are other methods where basically you could take your design, you could put it on an FPGA, and then you can test it for larger number of test vectors. However, for complex designs, the coverage is still very low. The third is like formal verification techniques where we build models from and then give guarantees whether the design is correct or incorrect. And this basically allows for complete verification. However, it is very expensive in terms of resources, so it needs to be seen where it can be applied and where it cannot be applied. Okay. This work, which I'm going to explain, is based on Boolean satisfiability. And the idea is like, let's say you have some real problem that you want to solve. In our case, it is verification of the mapping that is obtained from the simpler tool. So you take the map, basically your problem, you build a SAT instance out of your problem, and then you give it to a SAT solver. And what the SAT solver will do is it'll give you either that there is no satisfiable assignment to the SAT instance, or it will give you some assignment for which it satisfies these Boolean equation by satisfying it. I mean, like if you what values of the literals should take so that this equation which I'm showing here becomes 1. And here is like, for example, one SAT solution, and then you can basically use the solution to do some real world to the problem that you are basically applying. So this is like our overall flow of using Boolean satisfiability. And that is what we are basically have also done in our work. Just a brief motivation. I know we are in MIM talks, but the typically von Neumann architecture looks like this, where you have your compute unit, which is away from your memory. So the idea is you fetch the data from the memory, and then you do the computations in the ALU, and then you basically store back the data into the memory. However, what in-memory computing we do is we do the computation where the data is stored, that is in the memory itself. So And in this work, we are going to use the simpler tool. The simpler tool does the mapping of your design using this two gates called magic NOR and magic NOT. So I will just take you through how the NOR operation and the NOT operation happens in the magic design style. So you can see here, let me see if I can get a laser pointer. Yeah, so this is basically your output memristor. Now this output memristor is initialized to first a low resistance state. And then your input vectors are loaded into the memristor IN1 and memristor IN2. Then after that, you apply a execution voltage where this node is connected to ground. And if either of these memristors are in the low resistance state, that is, then there's a path basically which exists from Vin to through memristor out to the ground, and this changes state and it becomes 0. So that is how the NOR operation is done. In case of, while NOR is itself functionally complete, however, NOT operation can be done using only two memristors. And here what you basically see is you have your input memristor and you have your output memristor, whatever will be the value here. So if this is in the, if you put a value 0 here, that means if this is in the high resistance state, and like I said here also, you need to initialize this memristor to a low resistance state. Then not enough current will flow basically to flip this memristor. So it remains at 1. However, when this memristor is having a logic 1, then if you apply the input voltage, then it will basically flip this memristor to 0. So these two are magic NOR gates. So they are also proposed by the same group of Professor Shar, who have proposed this tool called Simpler. So the idea is now you have this NOR and NOT gates. They are functionally complete. The idea is how do you map this gates, or how do you map any arbitrary design using this NOR and NOT gates? So, and our goal in this work is how do we then guarantee that the mapping that we have obtained is correct? So let's start with it. So this is the flow diagram taken from this paper, which basically proposed the simpler magic tool. And basically what you have is you have any logic function. And what you can basically do is you can implement your design in Verilog, and you can create a genlib file which has inverter and NOR2 gates. In the paper, they also show with NOR4, but we will limit only to NOR2 and INV gates. And then you can give it to the ABC synthesis tool, which gives you an optimized NOR-NOT netlist. And these NOR-NOT netlist can be then given to this mapping tool, which is called Simpler Magic tool, which then gives you at which time instances, which memristors need to be executed in what order you need to do the operations, basically, so that you can implement any function. So this is a brief um, idea on how the Simpler Magic tool works. And this is open source, so like you can download and use it. And so basically, I will just take you through one motivating example. So what happened was like this is a design. This is like a subset of the parallel prefix adder. And you can see here that this design's Verilog implementation is shown here. Uh, and after that, this is the mapping that Simpler tool gives. And you have here basically, as you can see here, you have NOT operations and NOR operations. NOT operations require one input memristor and one output memristor, whereas NOR operation requires two input memristor and one output memristor, and also gives you basically the time instances at which the operations basically needs to be done. There is also like a line called initialization, because as I said, to do the operations in using the magic design style, you need to initialize your output memristor to a low resistance state, and then you can perform the NOR and NOT operation. Here we will see that the simpler gives output like M0 and M0 for two outputs like G out 0 and P out 0, which are basically incorrect, whereas they should be M2 and M3. This is what we found, but I will discuss it a bit later in the presentation, why this happens. So this was our proposed verification framework. It has three portions. So first, I will discuss the mapping part. So this is basically just using the simpler tool. So what we did here is we took the Verilog benchmarks, we synthesized them using UOSys to generate the BLIF, which we then gave to the simpler tool. And the simpler tool basically gives the mapping, which I showed earlier. The simpler tool gave us the mapping. then we had to formally verify whether this mapping is equivalent to the Verilog design in itself. So then what we did is we built a clause generator which takes the Verilog code, and it from that Verilog code, it generates clauses. So initially, when I presented the slide on Boolean satisfiability, I showed some equations like some Boolean equations. So this basically takes in the Verilog code and it generates a Boolean equation from the Verilog code. And then we take the mapping from the JSON file, and we again generate the clauses here using the mapping from the JSON file. Now, the idea here is that if the Verilog design and the mapping are equivalent, then you can pass it to a SAT-based equivalence checker, and then the SAT-based equivalence checker should tell you that, okay, these two are equivalent. In case they are not equivalent, then the SAT-based equivalence checker will give you a test vector, which basically tells that your the mapping generated is incorrect. And that we basically store here in result files. We will also see how using one of the warnings that Simpler generates in the log file, we were basically able to figure out why it was not mapping some gates correctly. And then we basically built a simple patch which corrects the mapping that is generated from the Simpler tool. And then we again fed it back so that we generate the clause from this corrected mapping, and then we again perform the SAT equivalence check to ensure whether they are correct or not. Now I will just go in a bit of detail. So typically your Verilog will have different kind of gates. You have NAND3, NOR3. It could have like a large number of gates. So we basically built a library of these large number of gates, and we wrote the clauses for each basic gates. And then in Python, like depending upon how the design were implemented using this gate, we basically built the clause for each output. Similarly, we wrote clauses here for from the mapping. Now in mapping, that is generated from the Simpler tool, you have not and nor operation. Here I have just shown not operation, but similarly you can do it for nor operation. We the initialization clauses where we said that some of the memristors, they need to be initialized to a particular Boolean logic state. So here you can see like they are written as 1. And here you can see that the output memristor here is like a not of M0. That is like one expression that you need to do. So basically M0 has the input, you invert it and you store it in M11. But to also check whether M11 was initially initialized or not, we AND it with M11. So basically this ensures that if M11 was not initialized in the sequence, then this operation will basically be incorrect. So this is how we handle the initialization of memristor before doing the operation. And so this is how basically we build clauses from your Verilog design, and we now also build clauses from your mapping. For the example that I showed, so the Python code basically for generating the clause looks something like this. And for mapping, we see that we have some clauses. So you have like some memristors, which basically gets your input values, and then some memristors, which are basically initialized to low resistance state, as you can see here. And there are NOR and NOT operations, as you can see here. But along with that, we always ensure that the output memristor is also present here while generating the clause, so that your they have the same value in that manner. And the idea is if this mapping and if this design are same, then the both of them should basically match. So after that, once you have the clauses, then we use the Z3 solver. So Z3 solver is available, which can be used in Python. And then what we basically do is we take the clauses that were generated from the mapping. So mapping is generated very nicely in the form of a JSON format using the Simpler tool. So you can actually take those. And from Verilog, then we took basically the clauses. And then this is how basically you can call for equivalence check in Z3. While we have used Z3 solver here, other solvers could also be used, because at the end of the day, once you have the Boolean equations of both of the files, like you can use any solver of your choice. Typically how the clauses look like. So here you can see the clauses that are generated from Verilog, they look like this. However, the clauses generated from the simpler tool, they only have NOR and NOT operations, which are ANDed to 1. So here you can see like how do the basically clauses from the simpler tool looks. And the idea is then we perform equivalence checking between these two. We took a lot of benchmarks in our design. Here I am just presenting 3 of them, but we worked through a large set of benchmarks in our paper, which you can refer to. And here we can see, like, for example, for C17 or C1908, this is the basically the count of clauses. So here, for example, C17, we had like 6 Verilog clauses, and NOR and NOT clauses are 13. And overall runtime of our tool was like 0.25 seconds, and there were no bugs, and so it did not require any patching. However, for this benchmark, we saw that there were some designs that were basically getting incorrectly mapped, and the count was 13. But for in our paper, we looked into ISCAS-85, ISCAS-89. We also looked into IWLS benchmarks and ITC-99, where we had like some cases where the mapping that was generated from simpler was, we found them to be satisfiable in all case. In like basically, it was telling that they are equivalent. In some of the circuit examples that we took, we were getting it to be not equivalent. And the reason for this non-equivalent portion was that in the log file when we looked, so simpler gives this that you have an unsupported operation called buff. So whenever you have like one input connected to your output, basically simpler tool is only taking into consideration the NOT and the NOR gates, but it does not take into consideration whenever you have your input connected to the output. However, it shows this in the log file of while running the tool. So we basically then used these warnings to then build a patch, because it was always happening for the cases that whenever the input were directly connected to the output, it was not basically considering it for mapping. So I will just take you here once to just show one thing. So as you can see here, you see that G out 0 and P out 0, they are just kept to M0, like they are just kept at M0, memristor 0. Basically, it didn't consider it while doing the mapping. However, they should be M2 and M3. But from this warning, we can figure out that which basically input they need to go to, and then it is a very simple patch. However, for all the other cases, we tried across benchmarks, simpler tool actually gave the correct mapping. But this was one corner case where we figured out that it was not working for us. So we then built a simple patch. And this is basically what the patch generator does. And after patching, we then again fed it to the clause generator. And basically what we did was when we again checked for equivalence, then we got the designs to be equivalent. So this was like one of our works where we basically took the mapping tool, and then we built a framework around to check whether the mapping is correct or incorrect. However, our group also works on other, because in-memory computing can be done using different kind of logic styles. I picked up Magic because they have this tool which works really fast. Uh, you can just download it and it starts running. And it's also I experimented a lot earlier on using on the Magic design style. However, we also have majority based in-memory computing. So we have this work from our group where basically they figured out a verification strategy for using on majority based in-memory computing. And in one of the other work, we showed that, like I said, like SAT is one of the methods that could be used basically to perform the formal verification. However, for some data structures, for example, adders, binary decision diagrams are quite fast. So if you know that you are mapping adders to your in-memory computing, like you are generating a mapping, then we showed that the decision diagrams are like faster as compared to using the normal SAT-based verification technique. So you can also have a look at these works. And I think this is all, this is our group website. So you can go here. You can also check out some of our works that we are doing in formal verification for IMC and also for traditional formal verification methodologies. And yeah, this is all that I wanted to present. thank you for listening, and now I will take questions.
Please go ahead.
All right, so it's a pleasure to be presenting a compilation flow that we developed with the University of Notre Dame, called C4CAM, a compiler for CAM-based in-memory accelerators. I'm João, as presented before, from TU Dresden, and so yeah, as I mentioned, this was a collaboration from people from TU Dresden, from Professor Castiglione's group, and from Notre Dame, from Professor Sharon Hood's group. So we have heard a lot about MLs in the past few months and years, and how they are rising the computer demands. And following that, we also have an unprecedented rise in computing power for these emerging models, right? Which leads to a bunch of novel architectures that goes either from data centers accelerators to very low power for the edge. And like in general, all of them are trying to get very high peak performance for a very low peak power, right? So basically, all these accelerators, they are trying to build and solve a problem that is present in any accelerator design, which is to get the computation done with less memory access as possible, or sometimes reducing the memory access so you can reduce the total energy. And this comes from the fact that memory access, in terms of energy and even latency, is way more costly than the computation itself, to the point where computation sometimes comes almost for free. And that's the scenario where computation has been moving closer to the memory, where before you had computation outside of the memory. Now people are building plenty of memory capable computation, or even memories that can compute the data inside of the cells. So there are basically two types of computations here, and two types of architectures here. One is called compute near memory, and the other one compute in memory. So just for the sake of an overview, architectures like UpMem and other accelerators based on Samsung's HBM, they can be classified as a compute near memory architecture because they have a dedicated logic placed close to the memory modules. Not always this logic is implemented as close as possible, but still they can be classified by this difference between the traditional computer architectures and the proximity that those architectures are now bringing. The other type of computation memory, which is the one that we are more interested here in this webinar, or most of the webinars have been digging into this computation memory paradigm, is based on the interaction between cells. For instance, in meristic crossbars for computing dot product or matrix multiplication, or Boolean logic, as Shannon presented before, using the magic paradigm, and also content addressable memory, which is the focus of my talk and the focus of our work here. So different from meristic crossbars and Boolean logic, content addressable memory can compute or can do some associative processing by taking the data and then finding the address of where the data is in the memory. So basically, it works as a backward memory where you have to provide your data and you're gonna get the location. And there are many machine learning applications that can leverage this behavior, and some other domains like associative processors, automata processors, and even for implementing logic in memory. So especially for the domain of machine learning, CAMs have been used for implementing hyperdimensional computing, and has been shown that they can achieve orders of magnitude when we compare to GPUs. So that's basically the main motivation of why you want to process in these new memory technologies. Right, so content addressable memories, they also follow some hierarchy as traditional random access memories. And here we are going to consider banks, mats, and arrays. And then inside of an array, you're going to have subarrays, which are a memory grid with rows and columns, as in traditional memories. But they also have a pre-charge circuit, and they also have some decoders and some simplifiers in it. And typically, those memory arrays are 32 by 32 or 64 by 64. For several reasons, they should be small. Right, and these camps can also be implemented in different memory technologies, from SRAM to emerging memory technologies like RAM, MRAM, and in this work we are particularly considering FIFET technology. Right, so if you have this memory with a bunch of subarrays, one thing that you can do is to look for similar vectors in the memory, for instance. And when you want to do that, you're gonna have to take your large search vectors and split them into small subarray sizes. I mean, first the content that you want to take a look at, and then the query that you want to take a look at. You have to do this partitioning of the stored data, the data you're going to store, and the queries, right? And these chunks, they are going to be end up in the subarrays. So, but for doing that, we as programmers, we are used to write programs, let's say in Python, and we represent, for instance, a KNN problem in terms of high-level operations like matrix multiplication and top K and normalizations and so on. However, the device is not going to understand those primitives. They are going to understand only memory access, mostly write and read, right? And also simulators, the available simulators, they provide some sort of programming capability which is close to this device API, which you, like people as a programmer, don't have much time to understand what is going on there. So there is a bottleneck of how you're gonna manually translate an application to a mapping in an accelerator that is based on CAMs. So on top of this programmability challenge, there is a lot of things to be considered when you are mapping to an accelerator. For instance, what are the CAM types that you have in those devices, if they are going to be ternary CAMs or multi-bit CAMs or analog CAMs, and which type of similarity metrics this device supports. For instance, if they support Hamming, Euclidean distance, or they support dot product and cosine similarity. Also, there are different cell precisions that, of course, it is available and you cannot change in the hardware, but a general tool should take care of that, and should also take care of the trade-offs between accuracy and performance if you go from multi-bit precision to single-bit precision. And there are also several ways how you can map the data and how you can map the queries to this device, which is gonna end up with different utilization, performance, and energy characteristics. And yeah, just one more information here. There's also several ways how you can merge sub-results from the CAM arrays. All of this should be in the present handled manually with low-level APIs, which takes a lot of work and restricts the CAMs only to experts. And that's why C4CAM comes to help, which is this compilation framework that we develop on top of MLIR. So MLIR, just for the sake of a brief introduction, is a compilation ecosystem for reusable and extensible modules in a compiler. So it allows you to represent and transform intermediate representations in several steps, in several abstraction levels. They are called dialects. So at the highest level, you can have something that is close, for instance, to Python. And then as you lower your code to more device-specific abstractions, you can get to something that is close, for instance, to the CPUs, the GPUs, or FPGAs. And MLR allows you to write then these dialects and also transformations to go from one dialect to another, right? And this is especially important because when you have plenty of hardware targets in your system, or you want to allow that models that are written in Python can be mapped to any hardware, you want to have a compilation flow that is simplified. So C4CAM builds on top of MLIR, as I said, and we take TorchScript as input. And here is a short version of how a KNN kernel is implemented with normalization and top K. And then the second input of our compilation flow is an architecture specification of the CAMs and the hierarchy that you want to map your application to. Right, so this first part, the third part, is reused from MLIR, but then comes this second part where you have the computing memory abstraction. So the computing memory abstraction performs some pattern matching and rewriting by finding, for instance, where the matrix multiplication that can be done in computing memory, or the search that can be done in computing memory, they are written to abstractions that are easier to be understood at this level of the compilation. So, and then we lower to CAM, the CAM dialect here. And this CAM dialect leverages information and knowledge that only experts have and optimize for them. Right, so going a little bit deeper and how it is implemented, we use Torch MLIR, and to support, for instance, KNN, we had to include more operations like the top K operations and the normal operations into this to the Torch MLIR dialect. And then we had to, in the same dialect, we had to implement the search patterns for similarity search, and then so that this dialect can search and rewrite these patterns. And more to the CAM part here, we also have some partitions of the operands to fit into arrays, because at this level of the compilation, the computing memory one, what we see is only the operation and memory arrays in memory. So the SIM dialect also partitions the data into arrays. And here is I bring an example of this code. So what you've seen here as torch expressions are translated to the dialect SIM as a transposition, matrix multiplication, and also top K. And then it is further replaced by similarities according to the pattern that appears in the code. So here we have support for 3 types of similarity or distance, which transform the code into this version with only similarity. Then we apply some partitioning, which requires now to also include merge operations, because each array is going to output a partial result. Right. So now we come to the CAMP dialect. So the CAMP dialect is responsible for splitting the search vector, the queries, into CAM arrays. And it mapped these chunks of vector to sub-arrays either in a single for search in a single cycle or multiple cycles, which is a capability that can be done in these memories. And it also implements a more specialized merge operation. So I just wanted to highlight that in each dialect, we implement only what is important for that type of device. If this compilation flow was going to crossbar, it would implement only the operations that are seen in the crossbars, for instance. Right, so in the CAM dialect, we also have the implementation of several possible mappings. For instance, if you want to optimize for latency, you would unroll the loop of the search vector as much as possible. And then we can go to the evaluation section where we present results that were obtained through the simulator CAM-I, which is a simulator from Notre Dame a group who is validated against real CAM devices fabricated by GlobalFoundries. Our baseline for comparison is an NVIDIA GPU here. The use case that we evaluated were the KNN that I've been talking about, and also DNA read mapping and hyperdimensional computing. So all of those three use cases, they have as a bottleneck of the computation, the similarity search or some comparison of strings. Right, and in terms of data set, we have simple data sets for HDC, like MNIST, and also like in a bigger application, we have the DNA read mapping over the human genome. And for KNN, we have small classification tasks on some miscellaneous data sets. And some possible configurations that we have to play with are, for instance, multi-bit precision and different optimization targets that we're going to present it in next slides. Right, so the first part of the paper, let's say, is some validation of manual mappings and the C4CAM generated code. Right, so that is one important step to kind of calibrate if our generated code is giving good results or meaningful results compared to the manual implementation. And here you have HDC implementation for varying the bit precisions, for instance, for 1 bit, 2 bits, and 3 bits. And also varying the number of columns of the CAM arrays. Right, so main takeaways here is that, yeah, the validation is sort of accomplished with a comparable accuracy compared to the manual design. And we also notice as previous work that latency increased with this array size. And then we have some GPU comparison, which is not exactly new here because prior works also shown that CAMs can provide a higher, extremely high speedups and energy savings compared to GPUs. So it was again in the direction of doing some validation and comparing. And again, here we have KNN and some small data sets. And important thing here to compare is that 3-bit CAMs can achieve comparable accuracy to the GPU, which is floating point based implementation. And it exhibits already a good speed up. But most importantly, the energy savings that you can achieve using CAMs are up to 5 orders of magnitude. Of course, for larger problems, this is gonna decrease, but still we show in the paper, and you can take a look at that you can still keep 3 orders of magnitude for larger problems in terms of energy consumption. And that's because, just to add a little bit more information, is because compared to the GPUs in the CAMs, you can search across all rows in parallel, using which increases latency, but also improves energy, right? And so, but C4CAM can be used not only for compilation, but also for some design exploration. That's another feature that we added to it. So the CAM base, which is like the compilation flow for optimizing latency, can also be switched to optimize for power or optimize for density. And those are cases where are really important if you have a power budget to be within, or you have a resource constrained device, which just have a couple of content addressable memories to keep it really small. And yeah, and then we showed that you can do some design space exploration, varying the number of subarray size and varying the optimization target. And I want to point out here that this CAM power can reduce power considerably, which was not possible in manual designs, or it was too hard to obtain using manual designs, while still keeping the latency about the same. All right, so coming to the conclusion, CAMs, as in other computing memory designs, they have great potential, right? And in this work, we bridge the gap between high-level representations, for instance, written in TorchScript or some sort of group of Python, into these accelerators based on content addressable memories. Right. So yeah, it bridges the gap between what you can support in the hardware, which are APIs, device APIs, and high-level application descriptions. And it also enables rapid design exploration through power and area constraints. As future works, and this future work is kind of already in progress right now, we intended to support more heterogeneous CAM structures and integrate C4CAM in Cinnamon, which is another framework that is totally connected to C4CAM, and it's tries to generalize as much as possible how computing memory, computing near memory are represented. And then you have specialization from this framework to other hardware targets. So C4CAMs is in this sense a generalization for only CAM architectures, but there is more work to be done for integrating this part of computing memory framework to C4CAM. Right. So that's all from my side. Thank you for your attention, and I'm happy to take questions now.
Thank you very much.